The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Welcome to our webinar. Today's webinar topic is CSER 2 webinar. Let our experts run your FEA on your CSER 2 analysis, part 1 of 2. We will have the second part on December 17th. The registration for that will be up shortly. Our panelist today is Tony Paulin with Paulin Research Group. A quick reminder before we start, all attendees are muted by default, so if you have any questions, please type them in the questions tab. And with that, I would like to invite our panelist.
Good morning. This is Ryan Metcalf, the Director of Sales and Marketing from Paulin Research Group. I'd like to thank you for attending today. We're going to go ahead and give you a brief introduction to many types of models that where our FEA technology can provide benefits, and I'm going to have the microphone turned over to Tony Paulin at this point.
All set? Good morning. My name is Tony Paulin, and the topic of this webinar is practical advice on how to improve real-world CSER 2 models using FEA tools or common sense and hand modeling. Now, we definitely recommend common sense and FEA tools, but don't necessarily recommend hand modeling. So what we'll be focused on is common sense and FEA tools today. Now, we all know about B31.3 code guidance that discusses non-conservatisms in the code that we need to be aware of. And we all know about the B31 code guidance that tells us that we're responsible for the requirements of design and that we're responsible for the selection of the appropriate SIFs. We're not going to talk about those topics today because we've covered those in other webinars, and those webinars are available on the PRG website and on the Intergraph website. But the practical series of webinars that we're embarking on today and December 17th are designed to go essentially right to the answer. We want to bypass the theory. We think we've done enough of that, and we want to cover the quantitative rules and guidelines for how to specifically solve problems. So as part of helping you solve these problems, we thought that there couldn't be a better way to do that than by letting you send your CSER 2 models directly to us, and that we'd help solve them for you, all for free. So anyone registered for this webinar can submit one CSER 2 model. We'll review it and send a brief report describing the model characteristics and our opinions back to you. More details on how to do this will follow. All we need are one CSER 2 model that you think would be good to analyze using the more rigorous analysis or FEA for flexibilities and SIFs that we're going to talk about today. Now, in the second part of this webinar on December 17th, we're hoping to review some of the more interesting pipe stress models that we get and help give you a better understanding of the type of non-conservatisms and errors that you face in the piping code. So in earlier webinars posted on the Intergraph and PRG websites, we've asked, and I hope answered, the question of why should we look at the accuracy of our current pipe stress analysis? So in this webinar, we want to focus on the when and how we should look at the accuracy of our current pipe stress analysis. And then when we're finished, if you like, you can send us a CSER 2 model that you'd like for us to look at. So here's what we hope happens today. We present the webinar. It'll be available for you to download from the PRG and Intergraph websites so that you can get any parts of it that you feel like you need. Now, we hope there's a few slides that you'll want to print out and tape to your door. You can see what I taped to my door. Then we hope that when you're looking at certain CSER 2 models, you'll think about what we've talked about, and you'll think about things that the things that we've discussed that will be able to apply to the models that you're analyzing. Then when you find a particularly good CSER 2 model that does apply, we hope you'll email it to us, and we'll review it and send it back to you. And then on December 17th, we'll take a few of the interesting ones and go over them in a second webinar. So the basic types of problems that we see most often where FEA tools or where more rigorous analysis can help are related to code SIFs, code flexibility factors, and cycle-related errors. Now, the SIF errors shown on the left here we've listed before and outlined in earlier webinars, so I'm not going to talk about those too much. But we know that more rigorous analysis can definitely improve our SIFs. For flexibility factors, we know that for all intersections and for all directions, the flexibility factors are not 1, as they're stated in 2012 and earlier B31 codes today for intersections. So we can definitely provide more applicable data for branch connection flexibility factors. Those will become more important as the D over T gets bigger. We also know that for cyclic services, the safety factors we deal with drop down to a fixed value at about 3,000 cycles. So once we hit 3,000 cycles and have relatively high stresses, we need to be extra careful. And that's time when a tool like FEA tools can be used more readily. Now, we want to know, and we want to help you define what extra careful means. We want to quantify these issues so that we can put a measure together, and we called it the criticality count, that helps you decide when you probably need a more rigorous type of analysis. Now, the criticality count is a quantitative evaluation that should help you make a judgment call. We're trying to reduce the number of critical systems that don't get analyzed properly. So conditions and the criteria that serve to help us get thinking about what is important in the results. So let's go over the list that we see here and talk about some of the important criteria. Item number 1 is the D over T ratio. The D over T ratio is the number 1 parameter that should be looked at. The B31 codes in Appendix D give a limit of 100. That covers most of the pipe that you'll deal with. Section 3, for many years, used a D over T limit of 50 for primary load stress indices. And this was a bit of a problem. Now, the reason for the D over T 50 limit was because of collapse tests on straight pipe and the tendency to buckle at lower D over T ratios of around 50 instead of plastically deform. Now there's an adjustment in Section 3 to the criteria for D over T that extends up to 100, but for us, after running a lot of analysis and comparisons over the last 6 years, we definitely see deviations in elastic behavior when compared to test that start in the D over T of 50 range. And then, of course, definitely exist over the D over T of 100 range. Local instability, high SIFs, high K factors in these regions are definitely something to be careful with. And so that's why the number 1 item in the criteria is what happens when D over T is greater than 50. So when you're evaluating the criticality count, when D over T is greater than 50, the first thing you do is add the number to the criticality count that's equal to D over T divided by 25. Okay, so let's go to item number 2, high cycles. That's the next critical parameter. It is amazing how many pipe stress engineers don't record the number of cycles that their pipe system undergoes. They default to 7,000 and assume that that's conservative enough. As soon as you hit 3,000 cycles or 4,000 cycles or 5,000 cycles, you're really at the limit of the safety factor, and you can't be wrong. If you're at 100,000 or at 100 cycles, you can be way wrong in the SIF calculation, and what you do really doesn't matter so much. So we really need to pay attention to the number of cycles, and as they start to get high, about greater than around 3,000 to 4,000, we need to realize that the SIF and the K factor calculations need to be more important in those ranges. Let's go to item number 3. We add a high criticality factor of 4 for the pipeline codes. And that's because the allowable pressure stresses in the pipeline codes can be higher than B31.1 and 31.3. They use high yield materials to reduce the wall thicknesses. And there's just not a lot of experience for Markle type fatigue loadings, which is what we calculate with our pipe stress analysis for these high strength materials. So our criticality count penalizes the pipeline codes a little bit. If we look at item number 4, we penalize B31.3 with a criticality factor of 2 because B31.3 doesn't intensify torsional SIFs, and we know they should be intensified. B31.3, 2012 and earlier, doesn't adjust for D over D, and Note 11 tells us that B31.3 is not conservative for reduced branch connections when D over D is between 0.5 and 1. B31.3 doesn't penalize torsion, it doesn't penalize in-plane SIF, B31.1 corrects for D over D, it doesn't penalize torsion, it doesn't have the in-plane SIF errors. B31.1 is too conservative. And so while B31.3 isn't conservative enough, B31.1 is too conservative. Now in the next 5 years we think that there will be corrections to B31.1 and B31.3, but for now they haven't been made. Section 3 has made them. So for the less conservative B31.3, when we evaluate the criticality count, we penalize it. Items 5 and 6 are the D over D effects. Item 9, if you're over 700 degrees, you've got additional problems related to creep, and you don't want to be off in the stress calculations. Item 10, if you can't get fabricated components and you have to build your own tees for pipe, you've got a special set of problems. Vessel people, we know, do this all the time, but vessel welds are generally inspected more on a volumetric basis than piping welds. A lot of our piping welds, we can't even visually inspect them. So if we've got to fabricate our tees, we're a little bit more concerned. 90% of our test experience is with carbon steel. Here in the lab, when we test other materials, we get more of a scatter on the test data. We've got to penalize ourselves if we're not using low-carbon steel. Rotating equipment is a sensitivity problem. We can't be off with the K factors when we've got rotating equipment in the model. Item number 13 is probably it's an interesting one because I put it at the bottom because it's hard to figure out what it means. But it is a characteristic that affects our analysis the most. And it's something that we're going to see more in the examples as we get to them here in a minute. And this is, do we have a tight piping system or not? You'll notice that all the other criticality counts are 2, 3, some factor, 1.7. The highest is for pipeline codes of 4. If you have a tight piping system, we add a 5 to the criticality count because tight piping systems are where we see the biggest problems. Now it's interesting to look at items 14 through 19 because here what we do is we divide the criticality count by values when systems are low. The D over T is less than 25, your SIFs are close to 1, your K factors are close to 1, and you just don't have flexibility issues. So criticality counts can necessarily be low. Now the question is, are you going to send us a piping system to analyze for you where the D over T ratio is 17? Probably shouldn't because it's not going to help much. Are you going to send us a system where the number of cycles is 200? Probably shouldn't because even if the SIFs are higher, it's not going to really affect the practical solutions in the piping analysis. So if we go to the next slide, here's the collection of the critical data. Now it's really simple stuff, but it's sort of interesting that I think a lot of folks don't put this data together when they start doing a piping analysis. And the first piece of information is the maximum D over T in a piping system. Next piece of information is the number of design cycles. These are critical parts of the evaluation in terms of knowing when you can potentially have problems. So if we go to the next slide. There's a few other things that affect accuracy in the analysis. Probably the biggest one that would affect us most often is vessel connections. Vessels have the largest D over T ratios of anything in our piping systems most often. So if we've got vessel connections that are close to things that we're interested in, including the flexibility factors for those can affect our systems a lot, especially if the systems are tight. If you're buying welding tees from the lowest bidder, okay, that's probably not a good idea. Expansion joints, those require more comprehensive analysis. Fluid transients, pressure transients, rapid changes in temperature, pressure, those things definitely require more analysis. Or if you know that there's been a history of problems, that's when you need to pay more attention. So what we want to be able to do is we want to be able to identify the gorilla in the room. So essentially out of today, what we want to say is that all pipe stress problems are not the same. A whole bunch of them are wrestling with the cute little chick, but some of them are wrestling with the gorilla. And when we have the gorilla, that's when we want to really consider using something like FEA tools. So let's try to put this into a project perspective. So of all the piping in the line list, and you see this in the upper left-hand corner, probably about 10% of it needs to be analyzed. Now that's clearly a function of the facility and the operating conditions and so forth, but let's say that that's a good guess. So of all the piping in the plant, 10% of it may need to be analyzed. Now, generally of the 10% that's analyzed, only a small percentage of that needs extra considerations. So that's what you see in the middle slide. But of that piping that needs to be considered, that is probably some of the most important piping that you'll be looking at. That's the big gorilla in the room. So when you use FEA tools or any type of more rigorous analysis, in general that you should find that our normal calculations are on the left. So we've got a few recognizable gorillas, but a whole bunch of cute little monkeys. When we start doing FEA type analysis or improved calculations, what we see is that a whole lot of the piping systems stay the same. They're still cute little monkeys. Nothing changes. A lot of the piping, or some of the piping, turns into nice cute little chicks. The loads go down even more. The stresses drop even more, so the problems are easier to solve. And what we hope with FEA tools is that the gorilla in the line turns into a nice, lovable little bunny in the line. So now if we go to the next slide, what we want to do is we want to have a sense of when we need to take this more rigorous look. When do we need to go off onto the second branch? So this is the slide that shows in the upper left-hand corner the criticality count. In the bottom right-hand corner is the numbers that go into the criticality count. And then when we make the criticality number determination, here's the criteria we want to use. If the number is greater than 5, then maybe we need more advanced analysis. If the number is greater than 10, then we probably want to look at the SIFs and the Ks that we have and see how accurate our existing calculation is for them. And then if the criticality count is greater than 15, we probably want to run FEA tools on that system. So let's identify the most critical criteria. And excuse me for repeating myself, but this is the most important criteria. Number 1 is D over T. Number 2 is number of cycles. Number 3 is the piping system tight? You've got to be able to make that determination. And then, are there areas of the pipework that show to have relatively high stress? Because these are going to be the worst case. What we're going to see with some of the examples that we look at is that piping systems can be huge, but there can be local areas in the piping system where they're tight, highly stressed, and with large D over T's, and that's what we want to attack. Here's the D over T ratio chart. What you see in light yellow here is where we have D over T factors that are greater than 50. So there's not very many. Most of what you do just doesn't need to be looked at in any greater detail. If we go to the next slide, here are generic SIFs. Now, this is an interesting slide because here what we see are generic SIFs that are greater than about 4.5 or so, or greater than about 5, I guess. So that's where everything is yellow. Now, you can see there's higher SIF regions than there are higher D over T regions. In the bottom of this screen, you see the generic I factor and the generic K factor. If you want to make estimates for effective lengths, effective I factors, how big things are, these are reasonable estimates as a function of D over T and D over D to make I factor or generic I factor calculations and generic K factor calculations for you. This slide shows you again, and this is an attempt to emphasize the D over T ratio. As the D over T ratio for unreinforced T's get bigger, you can see what it does to the SIF. As the D over T ratio for welding T's gets bigger, you can see what it does to the SIF. So as the SIFs get higher, that's when the errors in the calculation are greater. So now if we go back to the circles, we know that of all of the piping, we're not analyzing most of the piping we draw, we don't analyze. Most of the piping that we analyze, we don't need extra consideration for. But when we need the extra consideration, we need to be able to identify the gorilla in the room or the hoodlum in the room. And that's the objective of this webinar. So step 1, we would normally run the Caesar model the way you would every time. Next, what we would do is we would take a look at the first part of the criticality evaluation, because then we know if we've got any high stress areas, we know if we've got any tight areas, we know if we've got any gorillas in that line. Next, we decide if a more accurate answer has any safety or economic implications. If the stresses are low, then we don't worry about it. If the stresses are high and we feel like we need to follow the FEA tools path, we press a few buttons, get a better Caesar model, and see if anything has changed. So this is what we're trying to prevent 10% of the time. Most of the time, you want to put the numbers in, you want to crunch the numbers in your pipe stress program, you want to see that your stresses are okay, and you want to move on to the next problem. Now, people are saying I'm crazy. Well, the reason most of you want to do this is because you're experienced pipe stress engineers. And an experienced pipe stress engineer doesn't use the analysis to tell him if the system is okay or not. He uses his judgment. And all he does is use the analysis because it's a system he's seen 100 times. He uses the analysis to verify his judgment. And for those problems, he can put them in, he gets the answer he expects, and on he goes. That's the way most pipe stress should be run today. But there are some complicated systems where the results are not so obvious, where our intuition isn't as good, where we have high D over T ratios, and for those systems, we need another path. For those systems, we need to put a little more thought process into it. We don't want to overanalyze, but we don't want to underanalyze either. So what we want to do is we want to be able to decide when we need path A and when we need path B. And if you take a look at path B, the thinker uses FEA tools. So we want to be able to use FEA tools to know when we need to do a better calculation. Okay. In the old days, this is how this two-path process was done. We would make the calculation, we'd see that there was a problem, we would decide if we needed to reroute the pipe or not. Rerouting the pipe involved adding steel, moving supports around, and 4 days later we hopefully had a solution. If we didn't want to go that route because it was a real pain to the project, we would say we want more analysis. We'd build an FEA model, we'd argue about the results, we'd try to get the client to agree, we might refine the mesh and hope the results didn't change, and then 2 weeks later we would hope that we had a solution. Now that's how it has been done. Now how it can be done today, we hope, is that with FEA tools we can run these calculations in just a few minutes. We can use the criticality number to try to decide when we need to go in that path, and we can make better solutions for the gorilla problem in the room in a very project-friendly amount of time. So it should be here. Okay, here. Yep. Sorry, I got lost in my sheet here. So the difference today with FEA tools is that it really only takes a few minutes to do the rigorous analysis, and that's the difference. We don't need to spend $10,000 worth of man time to see if a problem might be eliminated by a more improved analysis. With FEA tools, we only need a few minutes of man time to see whether we have a problem or not. Okay. This is the reason that we can agree to look at any Caesar 2 model that you send to us. We can check that model in a matter of minutes. One of the webinar planners said to me, Tony, you can't agree to review every model that users send in. That might be well over 200 models. And I told him that without FEA tools, we couldn't do this because it would take days to build these models and analyze them. But with FEA tools, because it just takes us literally a few minutes a model, we can go through this process. So let's do a quick review of some of the branch connection basics and then start looking at models that might be good for you to send in to us to review. This slide emphasizes D over T. D over T, D over T, D over T. It's the D over T ratio that produces ovalization, that produces high I's and high K's, and these are the areas where we have problems. Here is an emphasis that the D over T ratio and high D over T ratios and high D over D's rather, can give us high through-run K factors. We oftentimes in the past didn't consider the through-run loads as significant loads, but when the D over D ratio is 1 and the D over T ratio is high, we can get a significant amount of flexibility through the run pipe. With this next slide, I would like to emphasize the most important flexibility component in your piping system, and that is bends. The bends provide the majority of the flexibility, so when you're looking to improve your model, make sure that when ovalization is restrained around bends, when bends are next to bends, when valves are next to bends, when pipe supports are next to bends, and the bend can't ovalize, make sure that you call the bend a flanged bend, a single flanged bend or a double flanged bend. Getting the bends wrong in a piping system will affect the load distribution in the piping system more than getting the K factors wrong for branch connections. Also, on the right, we don't want to miss or forget the fact that vessel connections can provide a significant amount of the flexibility because they generally have the largest D over T ratios in the piping system. Okay, so here's a simple model. This slide shows drawings from 1978 literature from Schneider that illustrates how intersection flexibilities can affect piping systems. So this simple system shows a 21% increase and a 41% decrease in certain of the piping legs. If we take a look at the criteria that we talked about for this system, the D over T ratio is 33. It's below 50. So we say, well, we got a 40% change here, which would be pretty significant for a pump analysis. So why did we get this change? If we look at KD, which is the effective length, the flexibility factor times the diameter of the branch if it's the branch side flexibility, or D is the diameter of the run side if it's the run side flexibility. The multiple K times D is 43 inches in this problem. If we go up and look at the piping system branch, we see that the branch has 129 inches of total length before we get to the axial run. So what we're looking at is 1/3 of the length is added by the flexibility factor at the branch connection at the point where the moment's the greatest. So this little bit of K over D for this low D over T system pointed out that this is a relatively tight branch, locally branched or local piping system, this small branch in the horizontal direction. So this is a tight branch from this system's point of view. Let's go to the example in Chapter 38 of the ASME Companion Guide by Ev Rodabaugh. This example illustrates the use of ASME flexibilities Ki and Ko. What we've got here is an equivalent length of 82 inches, so the K times D here is 82 inches. The D over T ratio for this system is 63. It's greater than 50. We expect a lot more of an impact here. The branch runs are 9 foot 9 inches. So we've got 82 inches over 117 inches, which is about 70%. So of the flexibility in the Y direction for the branch, the flexibility gives us a total of 70 inches. So or 70%. So we've got a significant contributor to the overall length of the system by the effective length of the flexibility of the branch. So let's go see what the conclusion Ev Rodabaugh drew for this system. So when he analyzed this, according to Section 3, it was unacceptable. The stress was 107,000 psi without flexibilities, and it was easily acceptable. The stress was 19,900 psi when he added flexibilities. Now, Rodabaugh also stated something that was interesting, I think, about flexibilities, because he states that conservative flexibilities cannot be defined. Thus, the goal should be to get best estimate flexibility factors. We do see customers run FEA tools on every piping system. Now, we don't recommend that, but you can certainly do it. Let's go to another system, or these are two systems that we've looked at before, and the left one is WRC 329. So I'll go through them just quickly. This is figure 15. It shows here what Ev showed here, that this 12 by 30 inch branch connection caused a reduction in the load of over 800%. If we go to our evaluation of this, we see that the D over T ratio is 79. The K times D is 281 inches. That's a significant amount of the length of the pipe. So the fact that the flexibility is at the end of the branch where the bending moment is the highest, the fact that the effective length is very high, says that, yeah, this we would expect flexibilities to have a big impact on this system, and clearly it does. If we look at the system on the right, what we see here is that we've got not a two-anchor system. System on the left, two-anchor. Very clear what's going on. System on the right, we've got multiple anchors. We've got multiple branch connections. In this case, what happened is there was a 281% reduction in moments at one branch connection and a 242% increase at another branch connection. So if we go on and do the D over T analysis for this, we see that the D over T is fairly low for this, but the K over D is, well, that's still kind of small, 86 inches. But if we come up and look at the branches, we see that the branches are relatively small too. So looking at this system, for certain directions of load, these would be considered tight or locally stiff branches. So now let's go take a look at, and this is the kind of model that you would probably say, yeah, I definitely want to send that to PRG and have them analyze that if this is something that's got marginally high stresses in it. Now let's go to a little bit more realistic condition is, well, this is something that you generally would deal with. This might be your gorilla, especially if this was larger diameter pipe, because here you've got multiple operating conditions. So now you've got interaction between the different branches, and the branch flexibilities in a tight system will tell what stresses result in when these systems interact. So if we do the criticality analysis on this, for this, the criticality analysis, if I considered that the system not tight was 6.7, which is just over 5, which says, well, maybe we're interested in it, maybe not. But if we considered a tight system, the criticality number goes to 11.7, which says, yeah, you might want to think about that. So we can see that the criticality constant is definitely affected by the tightness of the system, and we want to get a good sense of when systems are tight or not, because, well, the stresses will be significantly affected by those things. Let's go to the next system. This is a rotating equipment model, so the cycles and the stresses aren't so important here. When you see these, the first thing I always do when I identify where the pumps are, and then I find where the T's are. And I say, are the T's close to the pumps? So in this system, I see that there's a T that looks like it's close. There's a big head that's not in Appendix D, so I'd need to run another tool in FEA tools to evaluate that, that elliptical head. And then there's other T's that are removed from the system, but there's a good chance that those aren't going to affect things very much. So let's rotate this around a little bit. So this is rotated around so we get a better look at it here. So here's the two supports. There's the one T. There's the second T that we were looking at up here. And there's the elliptical head, so there'll definitely be a flexibility factor there. But when we did the analysis, D over T was 42, K over D 210 inches. Piping is, okay, that's a pretty long length, but when we look away from the T, we see that there are a lot of straight lengths in this. The guy that designed this system knew that he had to put flexibility in to keep the loads off the pumps. So there's a ton of straight pipe here in the loaded directions. So these are definitely not tight piping systems. Now the interesting thing that affected this was the details of the supports. And the details of the supports are something that a good analyst needs to take a look at. And FEA tools isn't going to help you with that. You've got to have a good experienced designer put the supports in the right place for that system to keep the pump loads reasonable and to build them properly. With this next configuration, if we look at the stresses, you can see the stress ranges. This one was to point out the differences between B31.3 and B31.1 and using the FEA tools models and not using the FEA tools models. So what you see is that B31.3 gives us a stress range of 29 KSI. And B31.1 gives us a stress range of 70 KSI. Now, what causes the difference? Well, when you look at the system and remember what we said before, you can see that as that branch thermally expands, it's going to put torsion about that OLED. And we know that B31.3 does not intensify the torsion. So if we go to the next slide, here's a D over T value of 27. Here's the KD, relatively small. But the reason you would use FEA tools in this case is not because of the D over T ratios or not because of the effective lengths, but because the FEA tools has corrected the OLED SIFs. In WRC 329, Rotabal pointed out that the OLED SIFs in the B31.3 code today were off by about 2, and so that has been corrected. Whoa, somebody just logged into my sound deal here. Here's another example of how we calculate. Okay, let's go on to the next one. Wow, that was interesting. Okay, there's sound on this slide. Wow. Okay, well, we don't want to listen to this slide. Let's go on to the next one. Oh, let's go on to the next one. Okay. This one doesn't have sound on it, so I can add something to this slide. So what happens here is in this example was intended because the D over T ratio is high. What you see, D over T ratio is high, piping is short, so loads through the run materially affected the pump loads. So we put we didn't worry about the branch. Most people worry about branches when they worry about K-factors, but K-factors can definitely affect through run loads, especially when the D over D ratio is 1. D over T is high here. You can see the KD ratio is a very big number. It's big with respect to all the lengths in the piping system. So for this small system, we dropped the pump loads by 43%. Now, as soon as we increase those run lengths, very, very, very little change. So if you're going to send us a model and you would like us to tell you how much it changes the loads or the stresses or the SIFs in your system, you would tend to send us this lower model and not send us that higher model. This is the typical example of a tight piping system. Here what you see is no elbows, very little straight lengths of pipe, high D over T ratios, KD of 447 for a single T. There's 6 T's in this model. The T effective lengths are more than 3 times the straight lengths in this pipe. The stresses when we ran this with FEA tools, the stress range went from 55 KSI to 25 KSI. So when you see a system like this, the first thing I would hope that folks would think about is you would never analyze this system without using something like FEA tools. Never, never do it because the results are just way, way, way too far off. Next slide. This is a condition where you'll see interesting developments in tight piping systems, and this was with catch tanks, cryogenic systems, systems when they drain, some flare lines that will build up either sludge or liquid on the bottom and then have a hot gas blow over the top, sometimes solar heating, sometimes rain on refractory line pipes. What happens is you get a buildup of something in the bottom and something else on the top, so you get a circumferential heating pattern and bowing. The biggest condition where bowing occurs is in API 661 header boxes. The figure in the bottom shows you what happens as the box gets cold on the top and hot on the bottom. It, just like a thermostat, it bows and it will collapse or crush the pipe on top. So in this case, it's important. There's oftentimes intersections at the top. The intersections at the top, D over D is 1, D over T can be a little bit high, so that can reduce the SIFs in those models. When I look at this system, something else that I look at is I see a lot of what may be tight piping systems. I see little branch connections. So all of the things that we noticed in our criticality number spreadsheet might be brought up in this system. This system has a relatively high criticality number if we've got tight piping systems. If we go to the next slide, when we see something like this, we say, wow, that's pretty flexible. But whenever you see a whole lot of pipe, what you have to do is look for local flexibilities. So if we zoom in on the bottom part of that, what you'll see is that somebody put in a ton of supports here for some reason. They put the supports in and forgot that the support spec that he was using had guides on every support. So everything was over-restrained and, well, this system was overstressed artificially. Now, would FEA tools help you from making a silly mistake? No. But when you have systems that are over-restrained, that's another condition that can produce tight piping systems. If we go to this next line, here is the perfect example of an overly tight, small D over D, high criticality number piping system. What you see here is a small D over D ratio. When we get very, very, very small D over D ratios, WRC 329 says these are the SIFs for these in the run are obviously silly. What B313 and B311 does is shown up in the top. This on the top left image is what you have. You've got a very small bore branch connection. Because of the way that the code rules were written back in the 1950s and 60s, SIFs on the run aren't adjusted for the D over D ratio, so you're using the SIF for a size-on-size intersection for runs for very small D over D branch connections. So as soon as you add small vent lines, small drains, small takeoffs, oftentimes stresses in main runs will be overloaded. And so what happens in this system is we see this larger branch coming in from the left. So it's putting a bending moment about the main header pipe. It could potentially overstress the main header pipe in a completely artificial way due to the SIF from the pipe that's attached at 1990. In addition, because we don't see any flexibility here, there's very little flexibility in that small piping branch, is when this large horizontal run moves the large run header, we're going to crush that small pipe. So in those cases, it's very important to evaluate the flexibilities in the SIFs where the small pipe is attached to the big pipe so that we recognize where we've got real stress problems and artificial ones. If we take a look at what PRGIK that's a part of FEA tools would tell us about this, you can see the large run side SIF problem. The run side SIF reported in B313 today would be 5.7 for IIR, 7.3 for IOR, when in reality those numbers should be closer to 1.7 and 1. If we go next to the next system here, this is another typical problem where you've got long sections of pipe and small crossovers. The small crossovers, well, the SIFs and the flexibilities here when the piping is tight can be a little bit important. Here we see D over T values of 63, criticality numbers of 11, 16 if it's tight. That's a little bit over where we want to go. If we take a look at the next slide, what we had to do here, because when we put the correct model in, the system was overstressed, we needed to add a little bit more real flexibility to it. I say real flexibility because when we use the standard Caesar model for this system, you get what's in blue. So the standard Caesar model for, well, the standard model for any pipe stress program for very, very small D over D ratios is the pipe, the flexible pipe, the branch pipe runs from the surface to the center line. So the flexibility analysis includes that extra flexibility. For this particular configuration, everything was very stiff. So that little bit of extra flexibility on both sides of the line added enough bending so that we weren't overstressed. When we ran FEA Tools says that's not what really happens. FEA Tools builds what we see with the red piping system, so it puts rigid elements from the center line out to the surface for everything, because that's the way that the systems really behave structurally. So in this case, then, we put a lot more bending back on the elbows, and the elbows were overstressed. And we need a little bit more flexibility. So in this case, FEA Tools showed us where we weren't conservative with these small branch connections. So now in this system, we look at it again. Well, here I see local flexibilities. So in this case, we probably never worry about this. This is something that somebody analyzed. The guy that put this system in knew probably what he was doing. The guy that put this next system in, he just didn't provide enough of an offset. If he ran Caesar, he got all the extra flexibility from the surface to the center line, showed okay, not really okay. All right, here's another model. This is an example where we've got a vessel. You say, well, why am I worried about a vessel with Boeing? Well, if we go to the next slide, what you see is Boeing can definitely move the piping around. Go to the next slide. You can see that at the end of the system, go to the next slide, we've got a branch connection that's coming off the vessel that's definitely bending this very, very large D over T vessel. FEA Tools is not limited. The FEA technology in FEA Tools is not limited to D over T of 100. A lot of vessels are D over T's greater than 100. If you have this model in FEA Tools, or if you have this model in Caesar and you run FEA Tools, it will let you build this connection and analyze it properly for flexibilities and stresses. Here's a good example, because this is a pump. We see people send us these types of models and say, would you please run this through FEA Tools or an FEA Tools product like that we have that's called the PCL, and show me how it improves my pump model. Well, when we look at this, we say, what does this have that's in my criticality list, in my criticality count? Unless I've got flexibilities at the ends, at this end condition or at this end condition, unless I've got a vessel there that's got a high D over T ratio, there's no branch connections in that. There's elbows, there's 90-degree elbows, which the code does a reasonably good model or job of modeling. There's pumps. We said, okay, we've got a rigid pump down there. There is no flexibilities that FEA Tools will help us with there. This is a pump system. Most pump systems have relatively low D over T ratios. If the D over T ratio is low and there's no intersections, FEA Tools isn't going to help you much. Here's a system where it helps a bunch. What we have here is very tight piping systems and multiple intersections in the loop. This is a very good candidate for FEA Tools. In this case, again, very tight piping system with intersections. What we saw is that without K-factors, we were 154% overstressed, and with K-factors, after we've run FEA Tools in this model, we were 46% of the allowable. Let's take another look at a typical piping system, okay? Big piping system, the first thing that comes to my mind is the high SIF problem. If you run this model on Caesar without making any modifications, have no stress problems, everything is fine, stresses are all very, very low. If you look at the criticality count, if the stresses are less than 20%, you can divide by numbers. So if you've got a very low criticality count in that, you'd never worry about it. As soon as you start having higher stresses, or if you've got tight portions of the piping system, or if you've got these small D over D ratios where the SIFs are way off, now you want to start zooming in and taking a look at it locally. Here's another different type of example. Here we've got reactor piping. So we've got all this piping surrounding reactors. The reactor is the biggest D over T in this piping system. This D over T can be modeled using FEA Tools and Caesar. If we go to the next model, here's another pump system. This pump system goes up and expands into a branch connection. The piping system from the pump is fairly small. D over T is 63. K times D is 259 inches. When I compare that to the lengths of the piping system, I think I definitely want to run FEA Tools for this system. Another big branch connection, we know what to do here. It's a lot of pipe. What we would do is we'd run the calculation in Caesar, check to see if we have any high stresses, zoom along the system once we've got a good model of it, focus in and see if we can identify what we now hopefully see as very stiff piping, very stiff local parts of the piping system. Now if we go to, what I wanted to do was include severe cyclic condition discussions. The B31.3 code talks about severe cyclic conditions and gives you a number of criteria that you have to satisfy. It does say that you've got to decide, as the designer, you've got to decide if you exceed 0.8 SA in 7,000 cycles or other conditions that you as the designer determine will produce an equivalent effect. Well, I would argue that we've talked about a number of those today, and on this slide and on the next slide I give you some guidelines and some equations for evaluating severe cyclic conditions. So I would print those two slides out and stick them on my door if I had any room on my door. If we go to the next slide, this is another simple idea of what is FEA tools. So this is just the two-path process that we've talked about. One of them is no low stresses, no rotating equipment, low D over T's, no cycles. You're on easy street and you're solving relatively easy piping models. If you don't have any of those conditions, then FEA tools is a big help. Here are the things that FEA tools does. It's got individual finite element models for contoured fittings, for bends with stanchions, for bends with steel, for hillside nozzles, for pad reinforced hillside nozzles. All those things can be evaluated individually. The elliptical nozzle that we saw in that pump line, that can be evaluated in FEA tools, and you can get K-factors for those as well. So there's a variety of FEA models that are available to you in FEA tools. In the bottom here you see the Caesar translator. That's what we're going to run on the models that you send to us. You'll send us your model, and in 2 minutes later I'll have a translated model that had FEA run on it. So there's a lot of neat tools here. FEA tools is available today from Intergraph. So if from what you've seen you say, I don't need to send you a model, all you have to do is find your Intergraph salesperson and place an order, and they'll send you a copy of this, and you can start using it tomorrow. This is the last thing I'd like to say. There's will be an attendee Caesar 2 model submission. You'll be receiving a follow-up email from Intergraph or from us with instructions on how to submit your Caesar 2 model for review. So please watch for that email. When we receive your Caesar 2 model, providing we receive it before December 13th, we'll review it. We'll use FEA tools and the guidelines we'll discuss here, or we've discussed here, and we'll send back comments and notes to you based on our observations. So please feel free to send any size model and to include any additional particular questions you might have about the flexibility analysis, how you think we would recommend that you would model things, and we'd be happy to send notes back to you on that. Information clearly that we've presented here is based on our unique and singular experience at Pollen Research Group, and it may or may not apply to your particular situation. So it's definitely your responsibility, right, to use the guidelines here and make sure that they apply to your system and your circumstances. So I'd like to thank you for your time, and Rich, I think we're ready to start taking questions. I've got a better picture of me.
We were answering questions as they were typed in, so right now there doesn't really appear to be anything pending. There's a couple that were very specific about that vessel model and whether or not it had slotted holes and why did it bend the way it did, but I guess we could take a look at that after the webinar. Right.
Well, and the short answer to that is that it definitely did have slotted holes, and the reason that that's a great question. The reason that it bowed was because it was an LNG catch tank. So it had LNG that would collect in the bottom of it, so it would freeze. So the bottom would contract and the top would stay ambient, and that would produce the bowing. So the vessel literally bowed. So we modeled that with Caesar. We modeled the bowing in that vessel with Caesar.
Tony, this is Mandeep. Can you hear me?
Yes.
I was in India and I was presenting FEA tools, and I saw something that I wanted to share with the attendees. One of the clients had done a coker, piping system.
Right.
And in that piping system, as you know, there are a lot of cycles and high temperature.
Right.
And, they had eliminated all their elbows, or tried to eliminate it as much elbows as possible. So the coke, when it's going through the, right, they're removing the coke, it won't get jammed up in the piping system. So they replaced the elbows with T's.
Yep.
So now they've gone from a flexible system to a lot of intersections, and then using ASME code, they don't get any flexibility in their system.
Right.
So I thought that would be a perfect candidate for FEA tools because it's hot, it has cycles, there's no flexibility, or a lot of flexibility is lost by removing the elbows.
That is just like the example S303. That would be a perfect illustration. of how to run the software or why to use it. Actually, that's the one of the reasons, Mandeep, that we asked folks to send models, because there's a whole lot of little reasons for why you may need to improve SIF calculations. I mean, one of them is that you get, when you have a small d over d intersection, the extra flexibility that the code gives you now really isn't there. So in some cases, intersections become stiffer, but that's reality. From a guideline point of view, what we see is that for most flexible intersections, adding a flexibility at an intersection is about the same as adding one elbow, 190-degree elbow.
Yeah, I think, and it has real implications. And I was going through that, and the customer was sharing their feedback, how they had to, get their system fast, basically. And so I was thinking in my mind, if we had FEA tools a year ago, we could have helped them in their real, project.
Yep. There's
Tony, here's one. Someone's asked, is the numerical criteria you gave at the start published somewhere?
It will be. We are putting that together. We're going through more and more models here. I don't know if I can spill the beans on this one, Ryan, but we're putting an app together for it.
Shit.
So this will be an iPhone app and an Android app, and so I'm hoping that by December 17th that folks will have a criticality count iPhone app if they want one.
Great. Okay, here's another one. How can we consider the flexibility of gaskets on
Gaskets.
FEA model? Well, it says
Gaskets.
gaskets. It probably means gaskets.
So if you want the flexibility of a gasket, you want the flexibility of the flange joint, I guess, because the gasket interacts with the flange joint. And what we tend to find is that they're just not that flexible. But if somebody wanted to develop a flexibility for it, we have a program, I mean, it's part of FE Pipe, that builds three-dimensional volumetric models of flanges and gaskets. And it's got gasket models in it based on tests that we've done here and some tests that Flexitalic did. And I mean, because part of the interaction problem of flanges with gaskets is that for PTFE, for composition gaskets, for example, is those lift off. So you can't just take AE over L or EI over, 12L cubed. You can't take those numbers times the gasket area and the gasket area and get an effective flexibility, because the flange surfaces will tend to lift away. So the flexibility of the joint tends to be a lot of what is the flange. And so if that's a real concern, then I'd say get a copy of FEA Pipe and shoot me an email.
Okay. Here's a couple that are kind of similar. How to interpret for roof nozzles on tanks directions for in and out of plane bending, since equipment axis and nozzle axis are the same.
Well, for roofs, what happens is there's definitely an in-plane and an out-of-plane direction. The in-plane direction is the direction through the nozzle of the, if you take the right-hand rule and cross the nozzle of the axial axis of the nozzle, so you cross the axis of the nozzle with the line from the center line of the tank through the axis of the nozzle, that gives you the defined in-plane direction. And the out-of-plane direction is just axial crossed into that in-plane direction. And so for FEA tools, for example, where you can ask for flexibility factors for nozzles in heads that are off-center, those are the definitions for in-plane and out-of-plane that FEA tools will use. And they can be a little bit different.
Okay, can FEA tools be used or applied to non-metallic pipe like GRE and HDPE?
People do it. And the reason they do it is that the flexibility factors are a function of the geometry. So if you put the right modulus in and you put the right thicknesses in, you're going to get the right flexibility. Flexibilities and the K-factors are the easiest things to calculate. Now the SIFs, those are a different story. I would question the SIFs. But if I didn't have anything else, I'd use them. because they definitely give you, especially for large GRE intersections, they definitely give you a better idea of the SIF than B31.3 Appendix D does.
Okay, what's the best way to analyze an elbolet?
With an elbolet, I would get a copy of FEA tools and I would use FE bend, because it's got a connection on bends that you can take off the hole in the bend and it simulates very effectively an elbolet. And then, yeah, I would definitely do that, and then it calculates K-factors. So it will calculate adjusted K-factors for the bends, and then you would put those back into Caesar for that bend.
Okay.
Wrap it up. There was, I have one more question that it has come up. We talk about ASME codes, allowing the use of better applicable data, and then in EN piping code there is also a similar statement. But Tony, have you seen if other codes, allow similar methodology to be used, to use the SIS based on FEA?
I tell you what, that's a great question, and the only codes that we focused on so far, as you say, Mandeep, have been the EN code and B31. So I haven't looked at any of the other codes per se to see if they've got the more applicable data as part of the text. I mean, the other codes definitely have the same equations for SIFs, but you would also like it that they use the more applicable data terminology also. So I guess my answer to that is I don't know for codes beyond B31 and EN.
Here's another question. Can FE pipe calculate weld strength?
I mean, FE pipe in a sense has got a general purpose FEA solver in it that people can use if you want to spend more time. It's got a modeler in it that it lets you build generic systems, and the way folks do that today is they will build detailed models of the welds. There's a program there called Stress Plot that once you've got a volumetric model of a weld, it cuts stress classification lines through the welds. Once you get stress classification lines, you get the membrane and the bending stresses, and from there you can go to FATs, you can go to not AWWA, but you can go to a Section 8. So there's a variety of ways that you can analyze welds going to a lot of trouble. Most of the systems we analyze for piping and for, let's say, Nozzle Pro or FEA tools assume that the user's provided a full penetration weld and that the weld junction itself is essentially stronger than the attached thinner section base metal multiplied by a stress concentration factor.
Okay, here's another one. Is B31.3 Appendix D SIF table based on specific welds or weld sizes?
It's based on generic welds that were first put together in 1940s by Blair in England. Those welds were made over a 10-year time frame because he was interested in developing SIFs, and at the time they thought that gusset plates were the best ways to reinforce an intersection. So Blair ran unreinforced tees, pad reinforced tees, but a whole suite of gusseted welds, gusseted intersections, trying to get proper SIFs. So those were run from 1935, I believe, to 1945. So that was the first set of SIFs that ended up in Markle's work. Markle ran a series of welds in the 1950s, generally larger welds with Lincoln number 5 stick electrodes, welds that we think are end up being pretty good and match what the type of welds that we make today. So is there a particular type of weld? It's a Lincoln low carbon steel stick electrode that matches real well with stick welds, very, very good MIG welds or TIG welds from today.
Okay. Can FE tools calculate European reduced pressure welding tees?
Reduced pressure welding tees. I'm not sure I know what that means. If you could ask the sender of that email to send a little more detail to me and give me a reference in the EN code, I can go take a look and see if that's a phenomenon or a behavior that we address.
Okay. Okay, umbrella tank roof. Which type is considered a nozzle pro?
Umbrella tank roof. You know what I'm going to ask there is that the fellow would send in because what happens is you can put the nozzles in different locations in the tank, and depending on where they are and what they're close to, that's going to affect how I would suggest that the model be built.
Okay.
Okay, let's see, this is from Dave. Several questions. We're expecting FEA tools to evaluate components. Can you state that the tool is mainly for modeling components more accurately instead? Okay, yeah, FEA tools, it does have a component modeler in it, and the components that it models are bends with stanchions, bends with steel. It models pressure vessel heads with nozzles, pressure vessel heads with offset nozzles, vessels with hillside nozzles. So those components it evaluates. Contours, tees it evaluates. The FEA tools modeler goes through the Caesar model and pulls out all of the, if you ask it to, it pulls out all of the B31 stress intensification factors for branch connections and replaces those models. So it takes out the T's and it replaces the model. It replaces the stiffness model and the I factor model with more applicable data. So the idea is that the first thing we wanted to do was to get the calculations that we make for our bread and butter every day. We wanted to get those right first. And so that's what version 1 of FEA tools does. Now there's definitely a whole lot of things coming in the works for FEA tools version 2, which we hope is out in the first quarter of next year. So I guess we say thank you again, right? And we're...
Thank you, Ryan. Thank you, Paul, Tony, and thank you, Rich, for answering the questions there. Thank you, everyone else, for attending. And once again, the second part of this webinar is going to take place on December 17th, and we hope to see you back again. Thank you.